Good afternoon. So, did you guys have a good Easter? Let's see. So Tobias, you said tomorrow is your baseball game?
Yeah, it's tomorrow.
Okay. And then, but Weston, you're going to be here, right?
Yes, I will be.
Okay. All right. Well, and hopefully Jada will be here. All right. Do you guys have any questions before we get started?
I don't have a question, but I tried a different browser for the quiz
Oh
and
yeah.
it works. We're good.
Okay. All right. Good. Yeah. I don't know why that is, but sometimes it gives us weird things. Now, did you see the whole thing, or did you have to scroll over?
I had to scroll over.
Yeah. Okay. So it used to not do that. It used to you could just see the whole thing, just like how I uploaded it. But somehow, anyway, every time it does like little updates, um, like 2 summers ago when it did a major update, it broke all the links in all the quizzes and all the tests, and it was just unbelievable. Um, anyways, but I have learned things like changing browsers sometimes makes a difference or whatever. So anyway, so I'm glad of that. Let's see. Anything else? Um, well, I will say, let's see this. When I was looking through basically, I'm trying to finish up the guided notes for chapter 11, and then I'm going to be working on the final as well. And so I kind of have to decide if the final is going to be in 3 parts or 2 parts. So it, but we're going to finish the final on the 9th. So I have to figure out in the next day or two if it's going to be the 7th, 8th, and 9th, or just the 8th and 9th. I kind of just have to see if 2 hours is realistic. I have a 2 hour final. I have a 3 hour final. I kind of want to look and see which ones students have done better on, so we'll see. So, okay. Well, let's go ahead and get started. Today we are going to cover 10.9 and we may do 10.10 as well. Both of these are very extremely short sections. And I kind of don't want to rush chapter 11 because I think chapter 11 you'll find is easier, but the lessons take a little bit longer. But so I don't want to rush those. So we'll just see how things go here today. All right, let's see, we need to, okay, there we go. All right, so 10.9, we're looking at the convergence of the Taylor series. So this sort of combines the ideas. Section 7 and 8, we talked about the power series, Taylor series, Maclaurin series. And then we've been talking about convergence and divergence of series all through chapter 10. So this section sort of combines these two big ideas of chapter 10. All right, so we're going to talk about, start off with Taylor's formula. Okay, now you might say, boy, this Taylor guy, he just had the Taylor series, the Taylor polynomial, the Taylor's theorem. Well, and I guess, when you start doing a lot of math, you can name everything after yourself if you want. So anyway, Taylor's theorem is sort of like I call it the series version of the mean value theorem. All right, so the mean value theorem, just to kind of remind you what that is that says that if you have an interval, the slope of the endpoints is equal to the derivative at some point. Okay, that's the mean value theorem. All right. So Taylor's theorem then says it's kind of like the f of b, or like a y value, is equal to f of a plus the derivative of a times b minus a plus the second derivative over of b minus a squared over 2 factorial, etc. So let me kind of decode this. So this is saying at some y value, it's equal to another y value plus the Taylor series. Okay. So this is kind of what we actually write here. So this says if f prime has a derivative of all orders, then let's see, in the interval containing a, then for each positive n in each x in the interval. Okay, so this is saying that the value of the function is equal to, now, and so this is the Taylor series. So the f of a plus f prime at x minus a plus f double prime and so on. So this is the Taylor series centered at a. Okay, plus, and then if you might remember that when we did the Taylor series, that we did the dot, dot, dot at the end, because it actually goes on forever. Well, the difference now is after whatever, like if we're going to the third order or the fifth order or whatever, then we're going to say the end is r sub n of x, which stands for the remainder. Okay? So it's the Taylor series and then plus the remainder, because it goes on forever. Okay? So where the Taylor series is the next derivative, the next term in the Taylor series. Okay? So it's like another way of thinking of this is that we're saying that a function can be written as a Taylor polynomial, and then this r sub n of x is the remainder of order n, or even the error term. Okay, so I know this has been pretty abstract, what I've been talking about so far. But what we're going to do to determine if a Taylor series converges is we're going to look at the remainder, the r sub n of x. So if the r sub n of x approaches 0 as n approaches infinity for all x in the interval, we can say that the Taylor series generated by f at x equals a converges to f on the interval. And then you can say that f of x is equal to that summation because or equal to the Taylor series, because what we're saying is that the remainder approaches 0. So if that remainder, that error, that extra amount, yes, the series goes on forever, but if that amount goes to 0, then we're going to say that it converges. Okay? So if the remainder goes to 0. All right, so we did this Taylor series generated by f of x at e to the x. So you might remember we did that Thursday. Okay, if you don't, let's see. Pull out your books. Let me just show you a little shortcut. on these problems. You've got your book here with you. Okay, so open up the back flap. All right, and just kind of from the back, you see integration rules, differentiation rules. Turn the next page, then you see limits, vectors. You'll use that page in Calc 3. Okay, then flip one more and you see the series, page entitled series. And you see some of those tests for convergence. Well, then underneath that, it has the Taylor series. Okay, so here is the Taylor series, and we generated several of these last time. Okay, we did e to the x, sine x, cosine x. We did several of these. All right, so instead of going through it all, I'm just showing you where it is in the book. So if you just need the Taylor series for e to the x, there it is. Okay, so, excuse me. So what we're doing here is we're saying that, okay, so e to the x equals, and so here's our Taylor series to the nth term, okay? And then we're saying that the rest is our remainder. So what we want to do is show that that this series converges, okay? So then the remainder is like the next term. So we take this last term that we ended up with, and we're going to have the n plus 1 term, okay? And so now the coefficient could be e to the constant or whatever. So so in this case, it's going to be e to the 0, which is 1. All right? Now, so what we have to show here is we have to show that this is going to go to 0. Okay? That's what we have to show. We have to show that this limit is equal to 0. Because, see, 0 times a constant, that's going to go to 0. So this we have to show is going to be 0. Well, the main thing here to show that is to actually use this limit here that we did earlier. This was one of those 6 limits that I said that we wrote down, and anyway, on page 566. So this limit, the limit of x to the n over n factorial is 0. Okay? So just applying this to this, if we just replace n with n plus 1, let n be n plus 1, then this is going to be true. And so then if this is true, then that means the series converges, because it converges to e to the x, because what's left over goes to 0. Okay? So the real math involved here is when you write your series, then whatever your n plus 1 term is, you have to show that that limit goes to 0. All right? So let's see if you can do practice 1. Okay, so let's see what you've got here. So the Taylor series for sine x, okay? So this is going through showing you how we did the Taylor series. But you could look at there in the book, in the table that I showed you, that it tells you that this is the Taylor series for sine of x. Okay? Oops. Okay? So what's happening here is every other term has a coefficient of 0, and so we're only getting the odd powers of x. All the even ones go away. So that's what we get for our Taylor series. Okay? So we get x minus x to the third over 3 factorial plus x to the fifth over 5 factorial, etc. Okay? So everybody okay on the Taylor series for sine x? Okay, so now sort of the next term. Well, if so I'm just using k's there. The book is using x's, but sort of the next term that we have to find the limit of is -1 to the k times x to the 2k plus 1. Now, why 2k plus 1? Because 2k guarantees you an even number. 2k plus 1 guarantees you an odd number. So we're doing the odd numbers here over 2k plus 1 factorial. Okay? So that's sort of the next term. All right, so now we have to determine is this, can we apply this to this? And is the limit of this going to be 0? Well, how do I know if what about this -1 to the k? If I didn't have that, then this, we could apply this and we could get it to converge. So what about this -1 to the k? What do I do with it? Well, if I cover it up and then just look at this and say, okay, by this property here, this is going to go to 0. How can I justify that? How can I justify sort of ignoring that part?
Because it's being multiplied by 0?
True. This is going to go to 0, but so what's the thing about -1 to the k or -1 to the n that allows me to sort of ignore that when I'm testing for convergence?
Isn't it part of the alternating series test?
Well, kind of. You're on the right track. That this is the alternator. But what this does, if this is what makes each sign, the signs go back and forth. So if I cover this up, what I'm doing is it's like I'm testing for absolute convergence. And so then if the absolute values converge, then the series is going to converge in general. But Weston, your logic also would hold, I think, if you were to have to write that as a justification as why this goes to 0. Because if you were to pull this out front and say, let's see if I can write that. If I were to write this as, if I were to calculate -1 to the k times this limit as k approaches 0 of 2 to the k plus 1 over 2 to the k plus 1 factorial, then since this limit goes to 0, then your logic of saying, look, anything times 0 is going to also go to 0. And so I would totally buy that argument as well. Okay. Hey, how are you, Renelle? You come to say, hang out with Jada today?
Hello, Mr. Strong. She looks so lonely. I thought I would just come pay her a visit.
We are a group of lonely people here today.
You're a group of smart, lonely people. I love this calculus 2 that's happening.
Yeah, it's good stuff. It's good stuff.
It is.
Did you have a good Easter?
Yes,
Good.
so much. Lots of grandkids and Easter egg hunts and coloring, and it was
Awesome.
and lots of good. Feeling grateful for what it represents. How about you,
Awesome.
Jeff?
It was great.
Didn't you preach?
I did.
How'd it go?
People gave me very favorable feedback. So
That's fantastic.
if the text of my sermon was "The Road to Emmaus" from Luke 24. So
Very
remember
good.
that story. So
I
anyway,
do.
it was good.
Good.
All right. Well, let's get back to this. So actually, what just happened, Renelle, is that Weston just gave me an answer that I wasn't looking for, but that was equally good for this problem.
Very cool.
So
Way to go, Weston Lee at St. John's. Woo!
All right. So, all right. Well, let's go to this one. It says, show that the Taylor series for cosine x equals 0 converges for all x. All right. So this is just another example. So if we were going to kind of, let's do it kind of the short way, where I'm going to assume that you can write the Taylor series. And so we're going to just look it up in the book. Okay. And you can do this on the quizzes and tests. Just find where these series are in the book. So to see to check that it converges, we're going to be looking at this limit right here. So what do you think? Is this going to go to 0? Jada, what do you think?
Yeah,
Why?
because it's once you write the limit, will it simplify to x n over n factorial?
In factorial?
Yeah.
Keep talking.
And then the alternator. Can't you just do the same thing as a practice
What do
one?
you think? So, pretty good. Excellent. So, all of these have kind of the same structure, the same pattern. And so, if you get them to fall into that same x to the n over n factorial, just like Jada said, then you can say, okay, that part's going to go to 0. All right? Okay. Let's see. So in the notes it says since every Taylor series is a power series, the operations of multiplication, addition, and subtraction for power series will all hold. So because they're all sums and differences and products, you can add more than one series together. Okay? They follow the rules for algebra. So what I'm going to do is I'm going to algebraically manipulate 2 of the Taylor series. Okay? So this is one, and we're going to just find the first few terms of this series. 1/3 times 2x plus x cosine x. Okay? All right. So now, So here I'm going to just distribute the 1/3 and get 2/3 x plus 1/3 x. And now cosine x, I'm rewriting cosine x as its Taylor series. Okay. All right. So Tobias, you see where I got this? Inside the parentheses. Okay. So it's just using the Taylor series for cosine x. I'm just doing a substitution here. All right. So now as I algebraically manipulate this and just distribute the 1/3 x, I'm going to get 2/3 x plus 1/3 x minus, okay, so let's see, we get 1/3 and then x times x squared is x cubed, and 2 times 3 is 6 in the denominator, and so on. I'm just distributing here. So x times x to the 4th is x to the 5th. 2 times, or 3 times 24 is 72. All right, so then, now, if as I combine my terms here, 2/3 x plus 1/3 x is just going to be x plus x to the 3rd over 6 plus x to the 5th over 72, and so on. And so what I'm taking is, so I'm taking what this original mess here and rewriting it as a series, and then performing the algebra and combining like terms, and then just getting one series for it. Okay. Now there is, well, let's see if you can do that. All right. So for practice 2, you're going to try to combine e to the x cosine x. So e to the x times cosine x using the operations in algebra. So Renell, I'm going through my final exam schedule, and I don't need you to proctor for me this year.
Don't?
At White Mountain campus, because we have no
That's
Calculus
right.
2 students.
There are no students there. That's easier for you and me both.
Yeah, exactly. Maybe next year I won't be quite so mean to them, so maybe we'll have them, but we'll see.
Oh, shoot. Yeah, you had at least one student who probably should have gone on, who was doing really well there, but
Yep.
you know, I
Yep.
just saw Chan out here, and I gave him a hard time for you, Jeff. I just want you to know.
Good.
I said, you had it. He's like, I know, I did. I just wanted this semester off. So, anyway, I gave him a hard time for you.
Good deal. Good. I'm glad you would. I would do if I were there. So.
Then when these three get on to the university level and need Calc 2 for their degree, and
Calc
they can
3?
check that box, or Calc,
Oh,
where
right.
they,
Oh, I see
they're
what you're
Calc
saying.
2 now, they can check that box. If they already have it, they already took it, they will be doing a happy dance. They'll be like, woohoo, Calc 2 under my belt.
Well, well, Tobias's sister, Keziah, took Calc 3 for me over the summer, and when she got to her 4-year university, she was like a superstar.
That is awesome.
So
yeah, and especially if they're looking at any kind of a math-based degree, like engineering or anything like that, they're just going to be worlds ahead.
Because most of the time, those are like 5-year degrees because of the math.
Yeah,
and
it takes so long.
So if they're already done with their calculus, usually it takes a whole year off their schedule. So that's pretty cool.
It is cool.
All right, let's see how we're doing here. All right, so if we have our e to the x, this is our e to the x power series. This is our cosine of x power series. All right, so how do we multiply those together? How would you show multiplying two infinite things together? Two infinite series. Anybody have any idea? I mean, do you understand what I'm asking here? I mean, that we're trying to show e to the x times cosine x, and both of these, actually I left off the dot, dot, dot here. Both of these are infinite series. So e to the x cosine x, we have one infinite series times another infinite series. So how would you do that? How do you even begin to show that? Weston, what do you think?
I just took the first three terms of each and multiplied them together.
Yeah, that's brilliant, because see, the question asked just says find the first few terms. So you don't have to feel like you've got to do everything. All right? Do exactly what Weston says and just do the first few terms of each. So I'm kind of distributing this way. So I said 1 times like the first three terms. So 1 plus x squared over 2 factorial. And then the next one, I'm distributing the negative x squared over 2 factorial through. So I put the minus in front, and x squared over 2 minus, okay, so then it's x cubed over 2 plus x to the, let's see, wait, I'm lost here. Lost track of what I was doing here. Okay, x squared, x cubed. Oh, here we go. X to the 4th over 4. So that's distributing the second one. And now the third one, I have x to the 4th over 24 times 1 plus x to the 5th over 24 plus x to the 6th over 48. Now, you might see that some stuff, as you try to line it up, starts to cancel. So you have the 1 and the x, but see here you have x squared over 2. And then here you have minus x squared over 2. And then we have an x to the 4th over 4 with a negative in front. And that's going to cancel with x to the 4th over... actually, let's go ahead and... I simplified 4 factorial to 24, but since I didn't do the other one, let's keep it as 4 factorial so that you can see that it's going to cancel. So if we just write what we have here, we have a 1, an x. So the x squared over 2's cancel. So x to the 3 minus x to the 3 over 2. And then x to the 4th over 4 is cancel. And then we could keep going, but that's the first three terms there. So what I'm trying to get you to see here is that when you have these series and you are, I did one where we just multiplied here, but if you have to, where we added, but if you have to multiply, don't worry about the fact that, oh, how do I multiply infinite things? We're just going to do the first few terms just so that we can see what's happening here. Okay? All right. Okay, so so that's actually it for 10.9. So what I would like to do is do like the first part of 10.10, okay, which is still kind of the same in the same venue here. Okay. Okay, I'm actually going to do the second part first because I want Renell to see this second part, because this is actually one of the most famous ideas in advanced calculus. Okay, so I'm going to do part 2, and then tomorrow we'll go back and we'll do part 1, and then probably go on to chapter 11. So this is called Euler's identity. And it says, for every real number theta, e raised to the I times theta is equal to the cosine theta plus I sine theta. Now, you've actually seen that in trigonometry. At the end, when you graphed polar complex coordinates on a polar graph, you actually wrote them in this form right here, okay? Now, so one consequence of this identity is that ei pi equals -1. And we're going to actually prove that. And then we're going to end up with, if you rewrite this, is e to the I pi plus 1 equals 0. Now, what's cool about that equation, and what is just absolutely amazing, is that this equation contains 5 of the most important constants in all of mathematics. So e, pi, I, 0, and 1 are all in this equation. Okay, and that's called Euler's equation. All right, so we're going to actually prove this right here, Euler's identity. And so let's see if we can go through it. So I want to review just really quick the powers of I. Remember, I is by definition the square root of -1. So I squared is -1, I cubed is I to the 4th is 1, and then the cycle repeats. So I to the 5th, I to the 6th, I to the 7th, I to the 8th, and so on. Okay? So we're going to start off with our Taylor series formula for e to the x. All right? So either from the book or we can recreate it. All right? And that's what we end up with. All right, so now what we're going to do is say, let's let x be I times theta, where theta is some real number, an angle. Okay? And so what we're going to do is everywhere we have an x, I'm going to replace it with I theta. So then e to the x becomes e to the I theta, which is 1 plus I theta plus I theta squared over 2 factorial plus ... I theta to the n over n factorial. All right, now, as I square this out, I'm going to have I squared, which is -1. And so what's going to happen is every even power of I is either going to become 1 or -1 and go away. We notice in these even powers of the exponent, I don't have an I in there anymore, because the I squared or the I to the 4th becomes -1 or 1. But these odd powers, I still have an I in it. Okay? So basically, as I simplify these, I'm putting them into 2 piles. Where I have an even power, I'm putting them in this pile, and the odd powers of I, I'm putting them in this pile. Okay? And then I'm actually going to factor out the I. All right? Now, why am I doing that? Well, look at in the back of the book there, look at the Taylor series that are there. And can you see one that looks like this?
Cosine x,
And what about this?
sine x.
Sine x. So now if you substitute back what those Taylor series are, this is cosine theta plus I sine theta. And that's Euler's formula. And so manipulating these infinite series is kind of mind-boggling that you can, but that using these power series that we can show this is equal to this. And that's very powerful. Okay, now, so the last thing we want to do here today is say, now let's go to practice 2. So using that formula, write e to the I pi in the form a plus bi. So using the formula that we just came up with, this right here, e to the I theta, equals this. So using that formula, simplify e to the I pi. All right, so Tobias, when you've got it, let us know.
Would it be -1 plus I?
Close. Close. Jada, what did you get?
I got the same thing.
All right, you're also close. Weston, what did you get?
Just -1.
Yeah, see what happens here. If you let theta be pi, then e to the I pi would be cosine pi plus I sine pi. So what's the cosine of pi?
-1.
And what's the sine of pi?
0.
0. So your I part is going to go away. So that's why your answer is just -1. So then that's how, if now we add 1 to each side, then we get that famous equation, e to the I pi plus 1 equals 0. Okay. So, anyway, I think that's kind of cool. I actually didn't learn that, you guys, until like till my master's degree program is where I had that in a class, and I was like, whoa, that's pretty cool. But anyway, I figured you guys could handle it with your understanding of polynomial series. So anyway, if you really understood that, you're ready to go into a master's degree in mathematics. So anyway, we'll see. But that's pretty much all I have for today. We'll pick it up from 1010 part 1 tomorrow. So do you guys have any questions before we call it? All right. Well, thanks for working hard today. Appreciate your concentration.
That was pretty awesome, Mr. Strong. You're pretty brilliant. And I wanted to say hi to Toby, too. Hi, Toby. I never see the long calculus units much. Jada got it, too. She sees exactly what happened there. So she's right with you.
Oh, these guys are awesome. If I could just get them to take their quizzes and tests on time, they would be the perfect. They would be the perfect class. But
all right, you three, did you hear that?
anyway, y'all have a great day. Good to see you, Renelle.
You too, Jeff.
Thanks, Mr.
Bye.
Strong.
Bye.